So yeah, thank you for the invitation to come down. It's rare to get an opportunity to talk about something like this when you don't just have that 15 minutes and you have to write a paper and do all that stuff at a conference. So it's a bit more of an informal chat about it to a group of people where pretty much everybody wants to be there. This is also the thing. I kind of came into this area sort of almost by accident in that I never intended to address intelligent music production or automated music production, but it came up as a natural consequence of a few of the studies that I was doing. Hence how I added this little subtitle of you're going towards something. So my take on it might be a little bit different. And the nice thing about presenting last in a day is that you don't necessarily have to go through as much background about what is music production, what is intelligent music production, because we've got basically the best 5-talk introduction that could be possible to get. But I think in developing a intelligent music production tool, often there's some similar framework to a lot of this development, and my gross simplification and understanding of that framework is as follows: that there's normally some review of best literature or literature, and from this, you know, speaking to expert mix engineers or going through books and so on, there's some theories pulled out of it, something that you do that produces better quality mixes. And from that, you find some signal feature that might correlate a little bit to this quality, some signal feature that when you change, you get a better quality mix, for example. And then some method of either maximizing or minimizing this feature such that you maximize quality. And again, it's a very, very simple overview of how this, on the 3-step concept. But I've always felt that there were some limitations to this. For example, who's really been asked when the literature is being compiled or being read through? Are they really experts? Are they non-experts? Which would actually be better to speak to? And is it really the best practice? This could just be a semantic difference between best practice and common practice. It could just be that it's the common practice that's been investigated, and maybe that's something better to look at than best practice. Does this particular measure really map to quality, or would it be, you know, is one enough? Would you need multiple parameters? And this, of course, would depend on how the optimization is being done, but is there one particular optimal mix? For any given set of multitracks, is there one ideal mix, or are there multiple mixes that are equally good but different in some way? So the question sort of that bounces into my head after all this is just, well, what is quality? And without really knowing, having an understanding of what makes a good mix, it's very hard to do all the rest of that work. So I compiled a word cloud of a document that I wrote recently, which is a summary of the last 2 years worth of work that I've done. And after words like the and an and stop words, quality seems to be one of the most predominant terms. And a few interesting ones like work, because I think it was a chapter heading, so it came up everywhere. So I'm interested in the quality of mixes, effectively. And if to suggest that the automated mixing systems that exist are or not capable of producing content or mixes equivalent to real people, I think the best overview of evidence for this, which I'm surprised I didn't see earlier on, is this slide from a study by Brecht, showing all these human mixers and one sort of automated mixer at the end. And of course, there was the issue that I guess it wasn't properly set up for different songs and so on, but it's interesting that this automated routine is being beaten by every single real person, most of which were students, and then the 2 lecturers of the students. So the suggestion is there that, of course, obviously there's more work to be done and so on in emulating the creative processes of mixing music. So some of the limitations would be, in my mind, mainly to do with the space that's being explored, the parameter space, and how to find a mix in that space. Depending on the parameters being used, there might be lots of locations in the space that provide the same mix, or there might be mixes that can't be found in that parameter space. So there's a need for a space where every point is a unique mix, so you can just move through that and move through all the mixes possible. And then the question comes up of how you effectively search through that space. So that leads into the first little thing I like to talk about, which is called mixed space, interesting enough. It's a study of how people, the formulation of a space and how people explore it. One of the main inspirations for this was one particular figure in a paper by Mark Cartwright, Brian Pardo, and Josh. at the very beginning of 2014, and it was just this one graph, which is referred to as a three-dimensional space representation of a three-track mixing session using faders. And my argument is it's a very good representation of the fader values, but it's not really a representation of the mixing process. Because as you move through this space, it's not clear how the mix is changing, other than gains are being adjusted. A good way to illustrate this is just to go dimension by dimension. If you start off with just drum and bass and two faders, and as you move these two faders, move in this very simple Cartesian fashion of x and y. And if you move both faders down by the same amount, you get a point down here. And if you move them up by the same amount, you get another point here. And the suggestion is that these 3 points in this space all represent the same mix. They're all at different radii at the same angle. So rather than think about this in a Cartesian sense, just think about it in a polar sense. And at this angle, any radius will just be the same mix but at different loudnesses. And if you then were to turn up the bass with respect to the drums, you get a different angle. Any other mixes again along that line at different radii would just be that mix but quieter or louder. And this is generalizable to any number of tracks. When you have 3, you just would have your typical spherical coordinate system, where you have an angle that tells you about the blend of the drum and bass, and another angle which is the projection of that balance onto the guitar dimension. And the same thing there, the radius is just a master volume, effectively. To add vocals, I didn't really want to go to the effort of drawing a 4-dimensional Cartesian space in PowerPoint. There's an automatic function for that. It feels like there should be. That's the next bit of research. But you see that for any n dimensions, you can generalize to hyperspherical coordinates where you have n-1 of these angles and a radius. And again, I'm taking the suggestion that the radius is a master volume of sorts, and it's these angles that represent parameters of the mix. They're either just blends between instruments or blends between instruments and other blends of instruments in a stacked sense. So with these 4 instruments, vocals, guitar, bass, and drums, in that order, the 3 angles actually have some semantic meaning and importance. The balance between drum and bass is effectively giving you the rhythm section of this track. And the balance between that rhythm section and the guitar gives you the full backing track. And then 5-1 is the balance of the backing track to the vocals. And there have been some studies looking at the balance of a vocal on top of a backing track in isolation. And this is just arriving at a generalized view of this. So you're probably more used to seeing this side, but the conversion is a fairly straightforward thing once you get the conventions right. So from the track gains, you can convert into this space. So in order to obtain data to use, we created an experiment where people had these 4 faders, and they would be played a piece of music, and it was not mixed or poorly mixed, or some initial condition was imposed, which was the same for every participant. And they started mixing, and then as the audio was playing, they turned the faders, and we recorded the fader output as well as the audio output. And from that, then we were able to convert those values into this 3-dimensional space of phi 1, phi 2, and phi 3, which represent these balances. So what you'll see here is our 8 participants, who of course were all tested at different points in time. They'll all just be shown in the same graph. They start at the same point in this space, and they will start mixing, and they will move out and explore the space effectively. Up in the corner then, there's a dissimilarity matrix, which will show the distance between each mix and every other mix. And in the graph will be a time series of the sum of that matrix as a measure of how diverse the flock of mix engineers is at any given point in time. So the point highlighted with the number 8 in the color red and in bold typeface, you'll also hear that audio as it's happening, assuming everything works nicely. So have a listen and a look. goes on for another 30 seconds, but for the sake of time, most people had stopped mixing at that point, and then mixer 8 and mixer 4 took a bit longer, so they keep moving around. But what we see there is that a lot of the mixers ended up sort of in the same position as one another. So we used 3 different songs, and for each song there were 2 starting positions, which are just shown here as A and B. The arrows then, the vectors, show the direction and step size of the first changes that were made to the mix. So of course there's 4 tracks, and you can turn them up or down, so there's 8 things that you could possibly do at any given point in time. But people typically, when they heard that initial configuration, decided, the drums are too loud or the vocals are too loud, and they all did roughly the same thing as one another, but in different amounts. And because of that then, their second step was slightly different, their third step was slightly different. And after 12 seconds, they were at their most diverse. They'd all gone off in different directions, and then after that they slowly started to get more and more similar again. I did happen to show an animation of maybe the most cohesive result and the best result, which is these blue ones starting with A. There were quite high agreement about what the final balances were in that case. We see when they started at a different point, they ended up at different points. And there's a clear distinction in the middle between where they started at point A and point B. And this is to suggest that the rough mixer given effectively really influences the final mix. I think there is this condition by which something you're given first limits your ability to see other possibilities. And this seems to be the case here. So by taking over all songs and all points and all participants, the median values, the median balances of instruments, and just going back to the track gains, we then find something that's, I think, quite interesting, and this might look a bit familiar if you were paying attention earlier on, that the typical level for the vocals was minus 3 dB below the full mix, and so on and so on. And then this is striking parallels, slightly off the screen, to the results that Brecht had shown. There's a few more animations now. Roughly, almost precisely the same value for vocals, for bass, and then out of the kick, snare, and rest of drums, you get the same value for drums. And this says to me that 2 different tests with 2 different motivations and 2 different, a very simple mix exercise and a very complicated mix exercise, people had arrived at these same balances. That's listening to music for decades. They had just internalized, perhaps, what is the correct level for vocals and the correct level for drums. And it's good to see that agreement. The next step here might be to add more complexity to the model. Instead of just adjusting levels, they also have some EQ and up there at the top some panning. It's very easy to build this experiment, but very difficult to build a theoretical model on how to turn it into a mixed space, so that's still ongoing. But that's more or less the end of that section. So when conducting these types of experiments, there is always a question of, is it better to have maybe a few experts or a lot of amateurs, some bad mixes, some good mixes, in this varied amount? So, of course, you take a few experts or a few discrete people. They've all got different personalities, different colors and shapes, and they're in different moods. They get different points in time, which is represented by the rotation of the faces. And this gives you really interesting discrete mixes and discrete concepts, but it's very difficult then to interpolate between them and really know what the full dimensions of mix possibility are. And this might be easier to obtain if you had lots and lots of mixers, so they wouldn't actually have to be amateurs, it'd just be anybody, but you would get individually a lot of maybe not great and quite boring mixes, but you would be able to interpolate between them to estimate some sort of dimension along which they're all varying. And that's the motivation then behind this next study, which is a study of lots of mixes of the same song, definitely referred to as 101 mixes, because that's how many there are. So this kind of stumbled upon by accident maybe close to a year ago on the same website that we all use to find multitracks. There just happened to be an archived mix competition where there was 100 mixes of this song. It seems to be, it was precisely 100. And then there was the one original mix, which is where we get 101 from. And the beauty of this being a competition is that there was an eventual winner. There were some runner-up mixes that were chosen from a short list. There was more that were given an honorable mention, and there were a lot that just didn't make the grade at all. So we have these levels of quality or performance in this competition. And we wanted to see how these mixes differed from one another, and did those differences contribute to the outcome in the competition. So after downloading all the mixes, a lot of right-click and save as operations, there was then the process of feature extraction, which is a lot of running MATLAB and waiting. And the features that extracted were mostly the typical ones you see in MIR and various other things about spectrum, amplitude, stereo width. There is the ongoing question of what features do you use, because most of these features are developed for what I would call as like coarse categorization tasks, like the difference between a piano and a trumpet playing the same note, instrument recognition, or genre recognition. But in this case, you've got different mixes of the same song, where the instruments are the same, the lyrics are the same, the tempo is the same, and some of these features wouldn't really vary that much. So it's an ongoing thing to try and find out which features are useful here and relevant. After taking all these features in that 36-dimensional space of features, there were 3 out of 101 that we considered to be outliers, and removed those. And then folded back the winner and the 2 runner-up mixes into a high-quality category, and then we split it into 3 different levels of quality. So with the features, then we did a factor analysis in 2 steps. First was a principal component analysis, and the discrete plot is shown here. And there's always the question of how many components do you retain, how many different factors do you retain. Often it's a case of, look, where's the knee, and pick a point. But we implemented a few different numerical techniques to try and help make that decision a bit more objective. And 2 of them suggested 4 components, which is what we were thinking initially. One of them gave a spurious result of 1, because factor 2 and 3 are very similar. And so we decided to pick those 4 components. There were 2 out of 36 features that weren't significantly correlated to any of those 4 components, so we removed those. And then did a principal component analysis on the remaining 34 features, 98 mixes, with very max rotation, and just limited it to 4 components. And this is the discrete plot of that result. So you see that there's one dimension which explains most of the variance in the features we extracted. So when looking at which features are loaded onto these dimensions, the rotation was quite helpful here, that you see a lot of features are very strongly aligned to particular components. So we pretty much have a dimension of amplitude variation, dynamics, loudness, compression issues. Dimension 2 is mostly features of high frequency, spectrocentroid, roll-off, and then the highest bands of a few sub-band features. Dimension 3 is almost all the spatial features, and 4 is the low frequency information. So we're suggesting that for this particular one song, in all the mixes of it, there were 4 dimensions around which people varied that we can roughly call amplitude, treble, width, and bass in that order of importance. And in order to see whether these were significant predictors in the mix outcome, we used an ordinal logistic regression model, and found that the treble, width, and bass factors were important predictors of mix outcome, while amplitude wasn't, which was initially a surprise, because so much talk goes on about the importance of loudness and so on. Until I went back and read the text from the host of the competition, who said that loudness would not be a contributing factor in the mix decision, in the competition decision. So that we see that quantitatively then in this data, in this model. So looking at a scatter plot matrix of these 4 dimensions all plotted against the other dimensions, and we've colored and shaped them according to the outcome. If you look at them maybe 2 by 2, we saw that loudness wasn't really an important part of the model, because good mixes are sort of spread all over different values of loudness, from the quieter ones to the louder ones. But for dimension 2, which was high frequencies, the top is the ones that are, you might say, too bright, which was a common complaint about amateur mixes in general. And as mixes have less treble and tilt more towards the low frequencies, the winner, the runners up, and the shortlisted ones are all focused in that region. We see that the widest mixes were preferred, are more likely to do well in this competition. And then we got a lot of more and more narrow and eventually mono mixes. It was one mono mix. And component 4 then was about the sort of level of low frequency information. I found that around the value of 0, there's most of the best mixes, and then too much bass or too little bass was likely to produce ones that were not considered viable, possible winners in the competition. So looking back over all of them again, you actually see that the winner and the runner-up, one of the runners-up, the second runner-up was the original mix, probably for nostalgic reasons. But the winner and the other runner-up are right beside each other in this four-dimensional space, and roughly located at the point 0, 0, 1, 0, which is to suggest that the two of the best mixes had typical loudness, typical spectral tilt, typical amount of bass, and above average width. So these could be 4 rules upon which to help guide a mixing system if you wanted to sort of steer it in the right direction. Once you have lots of them, the most typical one is probably going to be one of the best. That does suggest something interesting, that possibly the best mixes are not ones that are so completely different from all the rest. And we do notice that the original mix is quite far in the corner of most of this space, which suggests that everybody, the other 100 people all heard it and maybe did different things. They didn't take too much inspiration of it. And that was actually another thing that the reviewer wrote after the competition. He said, "I'm surprised more people didn't take note of this mix." And again, we see that it's statistically quite different to the rest. So these 2 studies talked about, there'll be more on this if anyone's in New York, by the way, but these 2 studies, one deals with the population, the other deals with a space and population. It's a great bunch of lads. So if you think of a population and add a space, what you get, it's not your question, you get a population in a space. Population in space is probably a concept a lot of you might be quite familiar with. If any of you traveled by this methods of transportation recently, you're familiar with populations in spaces. It's not really the context, as interesting as I find this context, not really the one I'm going to discuss, but it will be the context of evolutionary computing, which is a series of optimization methods and search methods which deal with lots of possible solutions changing over time. And the idea is that you approach the ideal solution from a variety of angles, from this sort of groupthink idea. And it's particularly suitable to problems that are nonlinear by nature and not deterministic. And all of these are framed as being aesthetic design problems like structural design or logo design. An interesting application of this was also in sound synthesis, where there was a target sound, and the synthesizer with lots of parameters, and the parameters were optimized to get the closest possible to the target sound. And it's been used for quite a while in algorithmic music composition to try and find pleasing melodies in a design space. So if we consider music mixing to be more of a, not a compositional thing, but a design problem where you've got a few things that you control, and everything here helps you control your mix. And you've got well-defined parameters, and you want to design that mix, which could be the best mix or it could be your best mix, and that's actually a really important part of this. So how could this be done? When you're doing these types of technique, you have to evaluate how good each particular member of the population is, its fitness, how likely it is then to help inspire the next generation of mixes move to the space. And there's a few different ways to do that. Normally when it's an aesthetic problem, you might only have, say, a small number of possible solutions. And if it is something like a logo design, you can just show them to the user, and they'll pick, I like this one and this one, use those to help generate the next generation of solutions. For audio, that's very time-consuming, because in this case, you'd have to listen to, say, like 100 different mixes of the same song, pick the ones you like the most, and then do that over and over, which I don't recommend. The other way of doing it is to try and find some rule, some model by which you can estimate the fitness of each one. This could be based on findings from research, which suggests that people prefer one sound over another, and so on. A interactive approach might be a good solution, where you rate a few of the mixes, compare them to one another, and then use some rules to try and estimate the rest. Having a user-assisted system is probably an important part here, again, from a design point of view, where I don't think people want a black box where they upload the multitracks, press a button, and get their mix after having waited 60 seconds or so. That they probably want, if a person is using it, they might want to feel like they are somehow in control of what they're doing. There's the question of, is the system helping the person to mix, or is the person helping the system to mix? If that's the case, then actually we can train a system over time. As one person continues to use it, it would learn their preferences and become more suited to them as a person. Because each individual person using it, each mix engineer might, again, have their own sonic signature, which is a collection of subjective filters and objective filters, one based on their taste, experience, cultural context, and so on, and then also what the tools they're using, the environment they're in. And this relates also to how you might go about doing an experiment with mixing. If you want to randomly take mixes from all over the world or all over the internet, everybody's using different tools, and you don't have that experimental control. But if everybody's using the same tool, in the same studio, and the same desk and plugins, you won't necessarily, you might obscure the other factors and not see the differences between them. And this is just an issue of how much control do you have how much control do you implement an experiment when you want to study human creativity effectively. This is timed quite well, actually. So what can we learn from some other disciplines? This is the suggestion that we can learn things from other disciplines at this point in time. Evolution algorithms could be a useful way of exploring some mixed space when that space is defined. We started working on developing such a space that people can explore, and each point is a unique mix. So pieces have been put together in that order. And also this helps understand the overarching idea of the topology of design spaces. If you think of music mixing as being something that you're designing, and how does that space look? And that would apply to any task, whether it is software engineering or ballet dancing. There's some space that people explore as they're doing it. One other area that I think they're at a point where we can learn a lot from is probably music psychology, simply because it's hard to study music technology without studying music. So it's hard to study music without studying a whole lot of other things as well, unfortunately. So it's worth looking at the reasons people listen to music. And this is some research from this year about the adaptive functions of music listening, the reasons people listen to music that are good for them, apart from maybe to avoid social contact. That goes back to on the train again. People just go on, turn in. And we notice that the social functions and the one I can't pronounce, but the ones that make you feel good functions tended to vary actually with age, that the younger people were more likely to tune out from the world, whereas the older generations were more likely to just want to feel good and listen to music. But the reason this is, I guess, somewhat related, or the ones I'm particularly interested in are the affective functions, which are I listen to music to change myself in some way. It's change your mood or something like this. And the reason that this is maybe somewhat useful now is because, at least at first, when they're given the session, a mix engineer is a listener. And the first time they hear it, it's a passive thing where they're just listening to music, and then they would start to mix. And you may very well get a mix engineer who receives a session and identifies it and says, this is a sad song. I now need to enhance the sadness, make it as sad as I can make it. Or this is an angry song, I need to make it really angry. Or this is a happy song, and make it really joyous if you're making it for a commercial or something. And then maybe other mix engineers who say, this has not enough snare drum, or it's not snappy enough or punchy enough, and it is in very technical terms, perhaps. So in the first category particularly, the idea of mixing involves a certain amount of empathy, because empathy is the ability to recognize mood and emotion in other things and other people. So if an artist writes a song with a certain mood, records it to try and convey that, as a mix engineer, your job is to not obscure that mood by making inappropriate decisions based on that and so on. And it has been noted, again, quite recently, that certain scales and subscales of this visual empathy relate to particularly people's enjoyment of sad-sounding music. It turns out about a third of responses to sad music are positive and make people feel good. And this was particularly related to certain attributes that they might have in terms of personality type. So you might have one mixer who, when he hears a happy song, feels happy, and hears a sad song and feels sad, and another mix engineer who just has no opinion either way on either of them. And this might influence the decisions they make as they explore mix space, as they start mixing. It's also been noted that purely different personality types and cognitive types can often prefer different music. And this is possibly another consideration when doing a test. Open question actually to everybody who does mixing experiments. How do you choose the multi-track sessions that you're going to use to get people to mix? Is it just really like the first 5 that you find, or is it ones that all have certain instruments? In an experiment last year, we pre-selected multitrack audio based on mood of that piece of music. We tried to find things that were kind of neutral and balanced because we thought they would be quite malleable. People could adjust them in different ways. And this, which this research I don't entirely agree with, suggests that people are either very empathic, very systematic, or somewhere in the middle, and they prefer different types of music as a result. It would suggest that if you gave people in an experiment a lot of mellow music, some people would really like it, and some people would hate it. If you gave them intense music, you would get the opposite people, and there might be some certain music which wouldn't have too much of a bias on people. And again, this is a decision that you might make doing an experiment. You might want to provoke intense reactions, or you might want to try and remove that from the mixed decision process. Okay, so the other things that we consider then is just studies that involve lots and lots of participants, because if we're really studying how people react to things and how people conduct a task like music mixing, there's probably millions of people around the world, or hundreds of thousands who do that, and we need to try and reach a bit more of them in experiments. And it's good to see that there are now like the web audio evaluation tool, the idea of doing some of these tests online and reaching more people that way. And also just to, again, you can't study music technology without studying music. And all people said to me, you can't study music without considering emotion and the effect it has as people are conducting their mixes. The kind of thing here is that the perspective on the experiment can change things quite a lot. And by way of, I guess, summarizing the whole day, coming full circle on this, I've taken the initial blurb of today's event and changed a few key words that if someone from a different discipline was thinking about it. They might say audio engineering and music production are inherently creative tasks or disciplines or artistic disciplines. You might disagree completely on how technical it is. Often involving extensive training and the investment of time, processes involved implicitly require knowledge of music, first of all. I think it would help. And how to manage people in studio, and emotional intelligence, and these things. And they can present barriers to us, effectively, to people studying these things from a distance. And non-musicians, I'm sure. So I'd suggest that there's so much to this area of intelligent music production that we're looking at certain parts of it, and now over time, over a decade or so, realizing that there's other areas, other disciplines that could come in and be influential. And I think a lot of people have addressed that idea today. So that's the theme there, that there's quite a lot to this. We need to explore the design space of our own discipline and find out where the challenges are and where the future directions will be. So thank you very much for still being here at 8 minutes past 7.